Welcome to Scientific Research Methods Unlocked, where we walk through the end-to-end research pipeline from data collection to analysis and synthesis. In this presentation, I will guide you through practical frameworks for gathering reliable data, building robust models, and turning results into actionable insights, all while keeping scientific rigor and strategic impact at the center of every decision. A solid literature review starts with a systematic search and smart organization, using database strategies and referencing tools to manage sources efficiently. From there, we critically appraise methodology and synthesize findings to reveal gaps. And finally, frame testable hypotheses grounded in existing evidence so that new studies address real uncertainties and build on established knowledge. When defining hypotheses, we focus on falsifiability, specificity, and operationalization, distinguishing the null from the alternative and translating abstract concepts into measurable variables. Pilot data and theoretical grounding help refine formal predictions, while careful choice of directional or non-directional formats and clear statistical criteria ensure that outcomes are quantifiable and that inferences rest on sound, testable principles. Choosing an experimental framework means balancing control and practicality. Randomized, controlled trials remain the gold standard for causal inference. Quasi-experiments leverage natural variation when randomization is impractical, and pre-post designs track change over time. Each approach has trade-offs for blinding, replication, and sample size. So design choices should prioritize isolating causal effects while minimizing bias for a strategic impact. Observational and non-experimental designs offer powerful ways to study prevalence and temporal relationships when experiments are not feasible. Whether cross-sectional snapshots, cohort follow-ups, or efficient case control comparisons. Strong questionnaire design, representative sampling, validity checks, and ethical consent are essential, and analysts must account for confounding, recall bias, and limitations when interpreting results from these studies. Ensuring data integrity depends on clear protocols and modern systems. Regular calibration, documented standard operating procedures, and proactive quality assurance set the foundation, while electronic data capture, version control, secure storage, and role-based access protect information. Layered verification like double entry, real-time monitoring, and traceability from acquisition to analysis help detect anomalies quickly and preserve trustworthy data lineage. Statistical analysis combines descriptive summaries with inferential testing to rigorously assess hypotheses using t-tests, ANOVA, regression, or non-parametric options as appropriate. Interpretation hinges on p-values, confidence intervals, and effect sizes, alongside assumption checks and corrections for multiple testing. Pre-registering analysis plans and reducing data dredging are practical steps to enhance reproducibility and transparency in findings. Effective data visualization and reporting prioritize clarity and honesty. Choose appropriate axis scaling, include error bars or uncertainty measures, and use colorblind safe palettes to avoid misleading impressions. Match plot types to the question, tidy tables with clear captions, and adopt concise formatting so that visuals transparently communicate trends and support reliable interpretation, rather than exaggerating effects or inviting misreading. Ethical rigor underpins credible research, starting with participant protections like informed consent, privacy safeguards, and independent review. Research integrity includes avoiding plagiarism and fabrication and applying authorship criteria fairly, while data stewardship follows FAIR principles and discloses conflicts of interest. Together, these practices sustain public trust, validate conclusions, and ensure that scientific contributions have lasting strategic value. The IMRAD structure guides clear scientific communication by encapsulating key insights in abstracts, setting up purpose, and hypotheses in introductions, detailing methods and data collection, presenting results transparently, and closing with thoughtful discussion of implications and limits. Writing best practices, such as logical flow, tense consistency, and concise active language support peer review, constructive revisions, and effective dissemination across the research lifecycle. Peer review and quality control create a continuous improvement loop for scientific validation, beginning with editorial screening for scope and novelty, followed by careful reviewer selection that focuses on methodology and clarity. Iterative revision cycles with point-by-point responses strengthen manuscripts, and post-publication dialogue through comments and corrections keeps work accurate and responsive to community feedback over time. Transparent workflows accelerate discovery by combining open data repositories, pre-registered protocols, and shared code notebooks for early disclosure and reproducibility. Version-controlled analysis, containerized environments, and replication studies make methods verifiable, and publishing negative results contributes to cumulative knowledge, safeguarding credibility across disciplines, and helping the scientific community build reliable, cumulative progress.